Hello, good morning everybody. So, we were discussing theories of reaction rates, and it is a continuation of our last lecture. Now, in our last lecture, so this is basically 12th lecture. So, in our last lecture we talked about transition state theory on surface reaction, okay, and in that case we discussed indirect adsorption process, okay, and we ended at this expression that d theta a star dt, which is equal to P A pressure of A divided by N 0, that is the number density of sites available, times twice pi m k t kBt square root, and this corresponds to the collision on a surface, since the atoms are still free to move in 2 dimension, that is on surface there is collision. Suppose this is the surface, so atoms are moving around, although they are weakly bound, but still they have the option to move like this. So there is a collision. So, expression is similar to what we got from the simple hard sphere collision theory. Okay. Next we will move on to direct adsorption process of atoms. Okay. Now, in this case the reaction coordinate that describes the adsorption process is the vibration between atom and the surface. So, you have got the surface like this, and suppose you have got the atom which is bound over here. Okay. So, the reaction coordinate will be this particular motion. So, if this is your surface, okay, so reaction coordinate is this, okay, and the adsorbed atom has 3 vibrational modes, one perpendicular like this, another like this way or maybe that way. Okay. So, these 2 modes, these 2 correspond to on surface, okay, along the surface, and this is perpendicular to the surface, okay, and 2 parallel to the surface and 1 corresponding to the reaction coordinate which is perpendicular to the surface. And usually the later 2 vibrations, which are called the frustrated translational mode. So, these are somehow similar to translation. So, suppose if a vibration occurs like this, okay, on surface, so it may be very close to the translation on the surface, and it is given a new name, although it is not a true translation, but since it is really a vibration, it is given frustrated translational mode, and they are very soft. This means your kT, that is the thermal energy, is much greater than your frequency of vibration. Okay. Now, associative adsorption usually occurs without energy barrier. Okay. So, that is, in that case delta E, for all practical purposes we can assume this to be equal to 0. Thus, we can write the transition state expression for the rate arising out of direct adsorption of an atom via this transition state, applying the same method as used for the indirect adsorption. So, similar technique we will be following as we did for indirect adsorption. Now, the gas phase partition function which we would need to use in this case, designated by Q gas, of the atom is the same. However, since the atoms are immediately immobilized, so you have got the surface over here and your atoms are here. So, immediately after adsorption they will find their own site, that is the sites which are fixed for them. So, permanent site like that, something like that. It is not that in unlike your earlier case, that is indirect adsorption, that they will initially bind to the surface in a very weak fashion, and then they will move around the surface and they will find a fixed position, fixed site. But here now atoms will find their fixed positions initially at the very start of the process, okay, and they will get immobilized immediately. okay, on a two-dimensional surface. So, this surface is a two-dimensional one. So, some of them are here sticking out like this. So, it is a two-dimensional case, okay. And and we need to take the configuration of the adsorbed atom into account in the transition state, okay. So, this is the situation. So, the density of sites means, say this is one site, this is another site, say this is another site, like this, okay. So, density of sites per unit area will be equal to, now as usual, N0 is equal to m, total number of sites, divided by area, okay, which goes as 1 by a square, where a is the length, this side and that side, maybe something like that. So, m sites are now, now the thing is that all these m sites are not necessarily free. Maybe when we started our counting of time, maybe immediately before that, some of the m sites are occupied because of adsorption. So, in that case 100% of m, I mean, say if initially suppose there were 100 m sites. So, maybe 90 of them are remaining free, okay, and maybe 10 out of 100, 10 are at the very start they are occupied. Therefore, we give a new quantity which is defined as number of free sites, which is equal to m primed, okay. So, m primed is basically your, if you take a ratio. So, theta star is equal to m primed divided by m, okay, which is equal to 1 minus theta a, that is fraction available, okay, for adsorption. So, direct adsorption, now mechanism goes like like this. So, you see that A, first it gets immobilized, okay, producing a transition state of this type, and then this gets into this is activated and then gives rise to A immobilized star, okay, but N0 is equal to m by A, where it is 1 by A square, okay, it goes as 1 by A square. So, m is the total number of sites available, m primed is the number of free sites. So, you see these are occupied, these yellow ones are occupied, okay. So, out of say how many, 1 2 3 4 5 6 7 8 9 10, and here 1 2 3 4 5 6 7 8, that means out of 80, see 2 to 4 5 6 7 8 is shown to be occupied. So, 10% is occupied. So, remaining 90% is free for other molecule, I mean other atoms to get adsorbed onto the surface, okay. So, partition function, overall partition function Q double dagger is given by this expression, where m primed factorial divided by n, this is your activated, okay, factorial into m prime minus n factorial, n double dagger factorial, okay. So, this is your number of available sites, and this is your say number of activated molecules, okay, or activated adsorbed sites, okay. So, I mean these are the number of adsorbed gas molecules, okay, number of activated I mean molecules which are in activated state. So, this is basically, this corresponds to number of molecules which are, I mean atoms which are adsorbed, okay, times your this, since this is for your activated state. So, therefore, an n number of such activated atoms are there. So, therefore, your partition function will be corresponding Q double dagger to the power n double dagger, okay, and applying the same thermodynamical principle that chemical potential in the gas phase and chemical potential in the adsorbed state, that is your double daggered state, mu double dagger, okay, these are equal, and applying the Stirling's approximation that ln n is equal to n ln n minus n, okay, for large n, and we get the corresponding equilibrium constant for the the distribution of gas phase and the adsorbed phase. So, N double dagger divided by Ng, which is nothing but after certain manipulation you will be getting this expression. Okay. So, K double dagger, that is the equilibrium constant for this adsorption process, which is equal to m is the total number of m sites times this. Okay. Here we do one thing, we introduce the coverage theta for your activated, okay, which is equal to n double dagger divided by m of species in the transition state. Okay. This number of species, I mean this is for your transition state, okay, and in general this one is much less than this theta star state, and this can be ignored, and as a result of which theta star minus theta double dagger may be approximated to theta star. So, therefore, later on we will approximate this to simple theta star rather than writing this to, because this is very small in comparison to your this state. Okay. This is your activated state and this is your adsorbed state. Okay. So, activated means before means the moment it collides, then it first forms this and then this immobilized one get transferred to this one. So, this refers to this particular state. Okay. So, your expression, and if I approximate this too, then your theta star is nothing but 1 minus theta a. That is this is your this is the fraction that is in this state. Okay. So, your rate after your transition state theory, okay, is your this is nu times your equilibrium constant divided by into V by kT, because it comes from your this PA factor. Okay. So, you recall your earlier lecture on indirect adsorption. Let us go back to that. That will help you in recognizing the part. Okay. So, you see, so if you just remove this one, then your KTST is this, okay, nu K double dagger m V by KBT. Okay. So, that we are using here, okay, that we are using over here. Therefore, this is your K, because when you multiply this with your PA, that will give you the overall rate, okay, that is ddt of theta a star maybe. Okay. So, therefore, you write the appropriate expression for your K double dagger. K double dagger is this, okay, this is your K double dagger. Okay. So, then this becomes theta star minus theta double dagger times your vibration, one out of many, one is taken out. So, you are taking out that vibration, that vibration is perpendicular to the surface. Okay. Okay. And so and the other one is it has got this in the gas phase, because it is in the gas phase. So, gas phase has got only, since this is the case of atom, so gas phase has got only 3 translation degrees of freedom. So, it is in 3 dimension. Okay. So, now you then approximate this one to theta star. So, you end up to this expression, okay, because nu is equal to kT by h, okay, approximate, you can approximate this too. So, this is kT by h, is thermal energy kT divided by h. So, if you divide, I mean if you write in place of nu equal to kBT by h, then you end up to this expression. So, this is an approximation. If you think that this vibration which is responsible for reaction to occur has got the frequency kT by h, that is kT means thermal energy divided by h, that is an approximation, that is why you write like this. Okay. And then if you write the respective expression, for your this one, you get this one, because you see this is two-dimensional vibrational partition function, and this is a translational partition function in 3 dimension, okay, and with another exponential term is there. Okay. So, what we get from this, we get this expression, okay, that kb t divided by h nu in 2D for 2D whole square, because it is a two-dimensional partition function. So, two terms should be there, okay, and therefore, what we get is ultimately this expression. So, from this particular thing we get that it is theta, it is proportional to theta star, and other terms are there, okay. So, we write the respective expressions, then simplify as this, okay, and finally KTST comes out to be equal to this one, okay, theta star, okay, divided by n0, and there is one term S0T, it is called the sticking coefficient. What is sticking coefficient? I am coming to that, okay. So, sticking coefficient which is a function of temperature divided by twice by m kb into T, okay. So, basically now you write in place of theta star 1 minus theta as I told earlier, okay. So, what do we get? We get d theta a dt, that is rate of reaction, which is equal to KTST into Pa, and you write the respective expression for KTST from the previous slide, that S0T divided by N0 twice by m kBT into 1 minus theta a, okay, where St is given this expression, okay, Q double dagger 2D vibration divided by Q translation of the unit cell in 2 dimension, because unit cell means here it is a 2 dimensional case, therefore, your unit cell will be a 2 dimensional one, because it is on a surface, okay. So, here we have, so and there is of course, there is an exponential term in your KTST, which is which we already shown, this exponential term, okay. So, here what we have done, we have assumed that the electronic ground state of the transition state has been raised by delta E, okay, and we are referring to this to the partition function of the transition state's ground state, that is transition state has got the lowest level. So, that we are referring it to, and Q double dagger 2D vibration is referred with respect to the bottom of the potential, okay, and the above expression shows that the adsorption rate per area, per unit area, is the collision number for that area times the factor St, S0T, okay. So, the adsorption rate is basically your collision rate, the rate with which it is colliding with with the wall, times your this sticking coefficient, okay. Now, the sticking coefficient indicates how many incident atoms were successfully, okay, successful in going to the adsorbed state, that is not all of them are in the adsorbed state. So, suppose 10 atoms are colliding, so out of 10 will not stick to the surface, okay, maybe say 50% is sticking and maybe 50% is going out, okay. So, therefore, we are just introducing, it is a kind of probability factor, I mean not probability, it is an it is a factor that reflects that not all the collisions are successful in making those atoms adsorbed onto the surface. So, therefore, the sticking coefficient indicates how many of the incident atoms were successful in going to the adsorbed state, okay. So, it represents a fraction, okay. Of course, it is a fraction, because suppose there are 100 collisions, okay. So, 100 collisions per unit time. So, theoretically 100 should get attached, 100 atoms should get attached to the surface, okay, but that does not happen, it is less than 100, and that takes care, I know this S0 T takes care of that. Okay. And of course, it is a function of temperature, because these partition functions are indeed functions of temperature, therefore, it is S0 T. Okay. Next is so Q translation of the unit cell in 2 dimension, okay, which is basically this trans divided by m. So, unit cell means that is a squared cell in 2 dimension. Okay. So, you can write this Q trans unit cell ultimately to this a square divided by h square twice pi m kb into t. Okay. So, this is nothing but the translational partition function in a unit cell of area a square. That is if you confine an atom within an unit cell, then how its partition function will look like. Okay. So, that is represented over here. Now, to get idea of the value of the sticking coefficient that I talked about, okay, for direct adsorption, okay, we substitute some typical number and see means what is that coming out to be. Okay. So, whether this is very close to unity or it is less than unity, or maybe it is much less than unity, that we would like to know for some typical numbers, for some typical situation. Okay. So, we substitute some typical numbers and such that your A, this A is equal to 2.5 angstrom, temperature is equal to 300 Kelvin, mass is equal to 40 into 1.66 into 10 to the minus 27 kg for some typical atom, maybe argon. Delta E is 0 and h nu is 40 centimeter inverse. And if we substitute this number, if we plug in this number over here, okay, then you will end up to getting like 0.09. Okay. So, it is much less, you see, it is much less than unity. So, it reflects that maybe out of 100, if it is 0.09, then out of 100 9 collisions are successful, remaining 91. Okay. 91 is of no use, although they are colliding, atoms are colliding onto the surface. Okay. And one more important point that we should think of is the adsorption process and corresponding change in entropy. You see that if something is adsorbed onto the surface like this, before adsorption it had more degrees of freedom to move. Now, since it sticks to the surface, okay, so its restriction is more, its freeness to movement is reduced. So, if its freeness to movement is reduced, then of course, its entropy should reduce. So, adsorption always results in reduction in entropy. Okay. And there may be steric factor leading to reduction of S as well. Next is what if the regime between direct and indirect adsorption, if we are in between these two, because we have discussed 2 extreme situations. One is your indirect adsorption, means we talked about that in our earlier class and our earlier lecture, and right now we discuss direct adsorption. Okay. Now, what happens if we are in between? So, the atoms break free of site and starts to diffuse. Okay. So, atoms are now detached, okay, and becomes free, and it will start to diffuse. Now, if the potential is very weak or temperature is very high, potential means the force which binds the atom onto the surface. Okay. If this potential is very weak potential of the form this Vxy, since it is in 2 dimensions. So, it is xy potential, okay, has the form this cosine function, 2 cosine function, I mean it is a cosine function, there is another cosine function. Okay, so, if temperature is high or if the if the potential is weak, then atoms will travel freely. Okay. So, atoms will travel freely means the here and there it will travel, because temperature high means so h nu by kT or kT kBT is much greater than h nu. So, that means they will have the option to move around the surface here and there in 2 dimension. So, it is basically a 2 dimensional gas, although in kinetic theory of gas we have seen that atoms or the gas particles may move within your container here and there in 3 dimension. Okay. So, but here, since out of 3 degrees of freedom, one is taken off. Okay. So, therefore, this situation can be regarded as a 2 dimensional gas. Okay. And the vibrational partition function q double dagger 2d vibration then should be converted to a 2 dimensional translational partition function, okay, because it is moving around on the surface. Okay. And eventually the this part will have to be replaced with this part. Okay. So, what we get out of this, that we are back to the formula for indirect adsorption. Okay. So, direct adsorption, when we are in the regime between direct and indirect adsorption, situation is such that your potential is very weak, the force which binds your atom onto the surface, that is the potential surface, I mean potential function is the amount of potential or the force is weak. That is why it is called your potential is very weak, that is the force with which it is attracting towards the surface is weak. Or if temperature is high temperature means their restriction is reduced because its thermal motion is increased. So, thermal motion is will tend to compete with the attractive force, and ultimately if it is very high, that is if the thermal motions or the thermal energy is very high, then they should get free. Free means the restriction is not there. Therefore, your direct adsorption, where initially those atoms were confined, they are immobilized, are now a kind of mobile. Okay. So, that is why the situation is a 2 dimensional gas, okay, and your corresponding partition functions are now reduced like this. We have to replace this with corresponding translational partition function. So, S0T will have this expression. Okay. So, S0T is S00 into e to the power minus some delta E activation. Okay. So, overall it is a kind of overall. Okay. So, there is delta E and plus there is another perpendicular vibration, okay, frequency for your perpendicular vibration. Okay. So, here this q0 dagger 2d vibration, okay, refers to the electronic ground state of the transition state, and q2d transition state unit cell to the vibrational ground state of the transition state, this refers to. Okay. And we have combined the 2 0-point vibrations with the delta E into an effective activation energy. This is called your effective activation energy. Okay. This is your effective activation. So, you see we have combined this one delta E with 2 0-point vibration, because you see 0-point vibration is h nu divided by 2, half h nu into 2. So, it is basically we are referring to 2 0-point vibration, okay, because we have converted your 2 dimensional case your 2 vibrations into translation. Okay. So, that is why in effect we have added this much of energy to the overall activation energy, and that gives you this this expression, an additional exponential term. Okay. Now, the description of molecular adsorption is very similar to that of atoms. Now, we will move on to molecular adsorption. Okay. So, this description of molecular adsorption, we started with discussion on atom adsorption onto the molecular onto the metal surface, maybe, or maybe onto the surface. Now, what if we replace a polyatomic entity? Atoms are maybe in most of the cases monoatomic entities in gas phase especially, although there are exceptions to this. So, in general, for simplistic cases, atoms are thought to be monoatomic, but if it is polyatomic, that means maybe if it is a molecule or if it is an aggregate of atoms, then what will happen? So, description of molecular adsorption is very similar to that of atoms, provided we account for the molecular internal degrees of freedom. Okay. When you account, we have to account for the internal degrees of freedom, because in case of atoms there is no degrees of freedom, internal degrees of freedom, like vibration, okay, or maybe rotation. Okay. So, hence we need to consider how these degrees of freedom change on going from gas phase to the transition state of adsorption. That is the moment the atoms, molecules are in the gas phase, it gets adsorbed onto the surface. Okay. So, what will be the fate of these internal modes, that is vibration. Okay. So, the reaction coordinate is the vibration between the molecule and the surface. So, this is, say this is your molecule, okay, say this is your molecule, okay, and your reaction coordinate will be like this is your reaction coordinate. Okay. So, if this is your surface, so this is your reaction coordinate like this. Okay. So, this distance changes. Okay. So, as it does like this. Okay. So, the reaction coordinate is the vibration between the molecule and surface and is not included in the vibrational partition function of the transition state. And again we can distinguish two extreme cases. Okay. Now, indirect adsorption of molecules. Okay. We will be using the similar expression as we did for indirect adsorption of atoms. Okay. We use the similar expression that d theta A star dt is equal to d n A star dt divided by m is equal to nu k double dagger n g divided by m, and ultimately this is equivalent to k T S T into P A, gas pressure, and k double dagger is your n by n g, your q double dagger by q gas. Okay. So, this gives you like, so rate constant after transition state theory is this, okay, nu divided by kb into T into V, k double dagger divided by m. Okay. So, V, m and h is here. So, ultimately what we got is your q translation in 2 dimension, okay, and you see this is your double dagger rotation and vibration, these are the internal modes, okay, internal modes in the activated state, and of course there is a translation in 2 dimension. Okay. So, this way they will translate in 2 dimension. Okay. So, your expression is this and divided by q translation in 3 dimension, because it is in gas, see it is partition function corresponding to the gas phase, okay, into q rotation in gas phase, q vibration in gas phase. Okay. So, if we put the respective expression, you see it is 2D, it is 3D. Okay. So, we will be getting this expression. So, we are not in a position right now to go into the expression of this, we just simplified this term and taking this together we got this expression. Okay. So, that means your k T S T is this. So, overall d theta A star dt, okay, which is equal to KTST into PA, where PA is over here, and you write this part, you put this over here, with S0T is equal to ratio of this partition functions, that is rotation vibration for your transition state and gas phase rotation vibration. So, rotation vibration double dagger state and gas phase. Okay. So, notice that if the precursor is sufficiently loose means it is not very very much sticking onto the surface. Okay. That is, no change occurs in the internal coordinates. Okay. So, and the sticking coefficient will be very close to unity. That means, if it is a very loosely bound, okay, if it is a very loosely bound onto the surface, then as if we can think for all practical purposes that fate of your partition function is not much, there is not much change in the fate of your partition function. Okay. So, that means you can write for all practical purposes. So, this rotational one, this one is close to this one, and this one is close to this one, as a result of which S0T is very close to unity. Okay. So, for your loose precursor, if the precursor is loosely bound, then the situation is like this. So, adsorption is more likely if molecules are in the mobile physisorbed precursor state, okay, and retains the freedom to rotate and vibrate as it had in the gas phase. Okay. This situation corresponds to a minimal loss of entropy in the adsorption process. Okay. As if there is not much strong linkage. Okay. Although it is a kind of, it is these gas molecules are inclined towards the surface, but okay, but they are not means there is not much change in their mobile state, or maybe in their internal modes. Okay. So, that is why there is a minimal loss of entropy while the gas molecules are adsorbed. Okay. So, that is why your sticking coefficient, that is S0T, is close to unity. Okay. So, this happen in case of your indirect adsorption. Now, what happens to direct adsorption? Here the molecules land immediately at the ultimate adsorption site. Okay. So, they are landing onto the surface, wherever they will land, that is their immediate position. They will not move around any further. Okay. So, here the molecule lands immediately at the ultimate adsorption site without any possibility of movement on the surface. So, here the only degree of freedom that the molecule has in the transition state are vibrational. Okay. So, this is the only mode, that is the vibration. Okay. So, this is the reaction coordinate, it is vibrating. So, once it is adsorbed, it will not move this way, that way, or whatever. It will do only, say this it has the option only this way. Okay. Like this, suppose this is your adsorbed one. Okay. So, that means on the surface, so it will do like this motion. Okay. This motion is like this. Okay. So, it does like this. Okay. So, kind of this is your one. So, this vibration. Okay. So, this gives the expression which immediately indicates that the rate constant is smaller. Let us go to that, direct adsorption of molecules. Okay. So, you see, as usual, some of the sites are occupied with respect to the molecules. Okay. And your overall partition function Q in the transition state is this, and you are putting the similar treatment as we did for direct adsorption of atoms. Okay. So, KTST will come out to be like this, Q primed double dagger divided by Q trans 3D, because situation is different, that in case of your indirect adsorption, we could have written, you know, Q 2D trans, then Q double dagger, you know, double dagger rotation, Q double dagger vibration, but here we cannot write. Okay. And also out of this we have to take out one mode which is responsible for this movement. Okay. So, here you know theta star minus theta dagger is close to theta star, which is equal to 1 minus theta a as usual, and Q prime double dagger is the partition function of the transition state. From this the reaction coordinate has been excluded. This is the reaction coordinate I have talked about. Okay. It is not the total partition function, but one coordinate, I mean one mode is excluded. Okay. So, this leaves us with the following expression for the rate of direct adsorption. So, this is the rate constant and you know similar, but the thing is that this is S0t. S0t is something different. Okay. So, what is that? Now, you see that for your direct adsorption what we get, ddt of theta is kTst Pa, which is equal to this much into S0t into 1 minus theta, and S0t is this, where 1 degree of freedom less. Okay. So, this divided by Q trans 2D in unit cell, translational partition function in the unit cell, and of course, the rotational partition function for the gas and vibration partition function for the gas. Okay. Let us take an idea about the you know about the sticking coefficient. What is the typical value? Okay. The sticking coefficient for the direct adsorption process is small, since a considerable loss of entropy is there. So, if there is not a considerable amount of loss in entropy is there, then your sticking coefficient will be high. So, there is a considerable amount of loss of entropy is there, and when the molecules are frozen at the site, it is a kind of frozen. Once it gets a site, it remains over there for time. So, it is a frozen, it will not move anything, it has the option to just do this one along the reaction coordinate. Okay. Example is the dissociative adsorption of methane. Okay, has the sticking coefficient of the order of 10 to the power minus 8 to 10 to the power minus 6. It is a very small. Okay, it is a very small small quantity. Okay. Now, what is this Q primed double dagger? Q prime double dagger can be written as Q prime double dagger 0 with you know an exponential term, with an exponential quantity, and of course, there is vibration, frustrated rotation, okay, and frustrated transition. Okay. These are all arising out of the internal modes, okay, into exponential and energy term. Now, this 0 refers to with respect to the bottom of the potential of the transition state. Okay. So, you know this is the reaction coordinate. Okay. This is the reaction coordinate. So, you see we think of your carbon monoxide adsorption onto some metal surface. You see that this is the reaction coordinate, along with this can vibrate. Okay. Okay. So, CO, this is your CO vibration that may happen, that vibration may be responsible for some for further reaction to occur. So, this is your you know this is one normal typical carbon monoxide vibration. So, actually the reaction coordinate is this one. So, it is bound, so like this. So, this is your molecule, this is your surface. So, this is where you know in this region you know it is changing in distance. Okay. This is your frustrated rotation, okay, x rotation, this is frustrated y rotation, okay, like this one, the other one, initially frustrated x rotation is this, y rotation is this, okay, like this, okay, and frustrated translation is a kind of, as a whole this one is moving, okay, frustrated translation, and frustrated Y translation is in this direction. Okay. So what do we get out of this discussion? Okay. Now, it is important to note that we are discussing here the adsorption process, and we are trying to apply transition state theory onto surface adsorption. Okay. Now, it is typically categorized into two, like one is your indirect adsorption, another is your direct adsorption. Okay. Now, for indirect adsorption, your what happens that it is loosely bound. Okay. So, loosely bound means it has got the option to move around onto the surface. Okay. So, it is loosely bound and corresponding sticking coefficient is high enough. Okay. So, it moves around the in a two-dimensional in a surface, and for your calculation of this partition function, you have to take out one mode which is responsible for your reaction to occur. That is the mode which is the mode which will be converted to a translation mode. So, at par with your transition state theory. Okay. And when it is the case of direct adsorption, and also one thing, that one is the case for your atomic adsorption, another is your molecular adsorption. Okay. So, atomic adsorption means it is a single atomic entity that is getting adsorbed, and the molecule, in case of molecule, you can treat the whole thing, that is theoretical treatment will be identical. Only thing is that you have to take into account that for molecules there are additional internal modes, translation, not translation, I mean rotation and vibration. So, these are the internal modes that you have to consider on top of what you have considered in case of atoms. So, internal modes are to be considered here also for your molecular adsorption. Okay. So, like if we go back again, that if it is the case of direct adsorption, even if it is molecular or even if it is atom, you see that if you look into the two-dimensional surface, that maybe initially some of them are occupied and remaining. So, your gas molecules or gaseous atoms which are going to be adsorbed onto this, they will be distributed among this available adsorption sites. Okay. And your adsorption available adsorption site, and another thing is that maybe for direct adsorption 100% reaction is not possible. 100% reaction means suppose 100 molecules are colliding, not 100 molecules will be adsorbed, maybe a certain fraction will be excluded, they will come out. Okay. And we have to for this we have to write the corresponding partition function, and then we have to treat them appropriately. Okay. So, so we see, and also importantly, when temperature is very high, then maybe if we are in a regime between direct and indirect adsorption, then if temperature is very high, or the potential force which binds your atom, okay, which binds your atom or molecule together onto the surface, okay, which binds your atom or molecule onto metal surface. If this potential force is weak, is not very strong, that it binds, okay, it is a very weak force, or if your temperature is high. Okay, if temperature is high, then their thermal motion motion will compete with your attractive pull. Okay. So, what will happen? They will move around. Thermal motion is so prominent that although initially they stick to one position, but what will happen if temperature increases? They will start to do some wiggling like this, and ultimately your firm position, the position which was fixed, will no longer remain there. It will just it will just to move around, start to move around like this. So this becomes this case of indirect adsorption, which is associated with some weak force. Okay. So this lecture, this particular piece of lecture where we talked about direct adsorption or indirect adsorption of atoms and molecules, gave you an idea of how how transition state can be applied to explain surface reactions, and how does it depend on gas pressure, how should it depend on temperature, okay, how the entropic factors are important in determining whether your sticking coefficient will be close to unity or will be very less. That is when it is the case of direct adsorption, then you see I have shown you that value is less. But if it is not a direct adsorption, if it is an indirect adsorption, it becomes higher because it is not attended by a huge loss of entropy. But when it is the case of direct adsorption, then it has to surmount its additional degrees of freedom, because once it is firmly fixed over there, then its other modes are now not in action. Okay. So in next lecture we will we will extend a little bit a little further in our next lecture, and we will close this transition state theory maybe in next lecture. So after that, after we are done with this transition state theory and theories of reaction rate, we will move on to, let us go back to what is there in the list. Let us see. Let us see. So after we are done with this, there is little portion left to be talked about with respect to surface reaction. Okay, we will move on to kinetics of some specific reactions. Okay, we will move on to kinetics of some specific reactions, like maybe. So under this heading, maybe some catalyzed reaction, maybe some photochemical reaction, like that. We will talk on that, some specific reaction. We will take up some specific reaction, and then maybe we will move on to kinetics of catalyzed reaction, like Michaelis-Menten, that is enzyme catalyzed reaction, and other reactions. Okay. So this much for today. So in the next lecture, we will conclude this theories of reaction rate portion, and we will maybe start with kinetics of some specific reaction. Okay. So till then, have a nice time. See you in the next lecture.